Swayam Prabha. Digital India. Educated India.
Welcome to the course Analysis of Variance and Design of Experiment. So, you can recall that in the last lecture we initiated a discussion on the topic of partial confounding, and we started a discussion through an example of two-square factorial experiment in which we had taken a setup in which we were trying to confound a factor in some of the blocks and in not in all the blocks, and based on that we were trying to estimate the factor when it is partially confounded, and we also estimated the factor, we computed the factor when it is not confounded at all, and then we compared its efficiency also, and based on that we had obtained different types of sums of squares and their variances, which are going to help us in the construction of analysis of variance. Now, in this lecture we will continue with the same example, and first we will try to see how the block sum of squares are going to be adjusted and they are going to be partitioned, because now you can see that the blocks are also divided. Once they are divided into replicates, and then each of the replicates is being repeated r number of times. So, the block sum of square has to be divided into the variation within the blocks and variation between the blocks, and so now how to get it done. So, that is the first topic which I am going to consider in this lecture. I will try to explain you, and so that we can complete the analysis of variance of this example, and after that I will take one more example on the 2q factorial experiments and try to give you some more idea, but the analysis, the approach, that is going to be the same as we have done in the case of 2-square factorial experiment. So, in that case I will be quite quick in the sense, because now we already have learned how to compute different types of factors, their sum of squares, their variances, etc. So, we begin our lecture and first try to see how we can compute the sum of square due to block in the case of partially confounded effects. Okay, so now if you can recall that in the last lecture we had taken this example where we had considered the 2-square factorial experiment, and we had confounded the effect A in the replicate number 1, effect B in the replicate number 2, and effect AB in the replicate number 3. And these are the different types of treatment combinations which are given to the different blocks. And after that we had said that each of this replicate, this is being repeated here r times, right. And you can see here that in the case of partial confounding, A is confounded in the replicate 1, but in replicate 2 and replicate 3 it is not confounded. So, A can be estimated from the replicates 2 and replicate 3, and similarly the factor B can be estimated from replicate 1 and replicate 3, because it is confounded only in the replicate number 2, and similarly the interaction effect AB is confounded in the replicate number 3. So, this can be estimated from the replicates 1 and 2, and means we are going to use all the R observations which are obtained from the different replicates, right. So, now what we try to do, we have obtained all the treatment sum of squares and their effects were estimated as arithmetic mean of the effects which are estimated from different replicates. So, now we are trying to consider about the block sum of squares in case of partial confounding. So, now you can see here that the blocks have been divided here into two types of blocks, when they are in the form of replicate and then they are being repeated, right. So, The block sum of squares will have here two components, due to replicates and within replicates, right. So, the usual sum of squares of block that we used to consider earlier, that is needed to be divided into two components based on these two variants. So, now we try to illustrate here that how the sum of squares due to blocks can be adjusted under the partial confounding scheme. So, we consider the same setup here, that there are 6 blocks, 2 blocks under each replicate 1, 2 and 3 and each repeated r times, right. So, now you can see here there are altogether 6 r minus 1 number of degrees of freedom associated with the sum of square due to blocks, right. That is the same thing if you try to use the concept of r star is equal to 3 r, this is the same thing. Now, the sum of square due to blocks is divided into two parts, the sum of square due to replicates and sum of square due to within replicates. So, that you will see that the degrees of freedom which are associated with sum of square due to replicate is 3 r minus 1 and with within replicates this is 3 r. Well, how to divide it, that I will show you after I try to attempt the partitioning it, right. So, now we introduce here a symbol that B I to be the total of ith block, that is the block total as usual, and R I here is the total due to the ith replicate, right. So, now if you try to see, I am trying to write down here the usual definition of the block sum of square that we used to use in the earlier cases. So, SS block I am trying to indicate it by here this subscript partial confounding, that means by C. So, that is simply 1 upon total number of treatments and summation I goes from 1 to total number of blocks B I square minus correction factor G square upon n, right. So, if you try to see here, how many blocks are here? 3 r, right. So, this will become here and 1 upon 2 square summation I goes from 1 to 3 r B I square minus G square upon 12 r, because there are altogether these many number of observations available. Now, what I try to do here, that I try to add and subtract here r I square with B I square, and then I try to consider this B I square minus r I square and this plus r I square is combined with the correction factor. So, you can see here this I can write down here 1 upon 2 square summation I goes from 1 to 3 r B I square minus r I square plus 1 upon 2 square summation I goes from 1 to 3 r I square minus correction factor. So, now if you try to see here how are you going to compute here this B I square. So, I try to express it as say B square 1 I plus B square 2 I divided by 2 minus r I square, right, and this factor will remain as such. So, now if you try to see this B j I is indicating the total of the jth block in the ith replicates and j will go from 1 to 2, right. So, now you can see here the sum of squares due to blocks within replicate, which is indicated by here W r is given by here SS blocks W r, which is here the first term here, and the second term is sum of square due to block in replicate, this is here the second term here like this. So, you can see. So, now you can see that in this case of partial confounding, even the sum of square due to block is also divided into two parts, sum of squares due to block within replicates and sum of squares due to blocks due to replicates. And yeah, total sum of squares remains the same as usual and is given by the similar quantity what we had done earlier. It is sum of square due to total triple summation y square I j k summation over I j and k minus the correction factor G square upon n, and n here is going to be 12 r. So, now you can see we have obtained here all the treatment sum of square and sum of square due to block and sum of square due to total. Now, SSE you can find by subtraction. So, now we have here the ANOVA table, right. And well, in case if you want to conduct the test of hypothesis, in this case that is going to be exactly on the same lines as you have done in the case of factorial experiment, right. So, there is no need to discuss it here again. So, in the case of this partial confounding, you can see that the sources are due to replicates, block within replicates, in which the sum of square due to block is now partitioned into two components, SS block due to replicates and SS blocks within replicates, and they are carrying the degree of freedom here, say 3r and 3r minus 1. And yeah, if you try to compare it with your earlier one, this is something like here, say r star and r star minus 1, where r star was equal to 3r. If you remember, we had compared the terms under the partial confounding with the usual expressions, right. And similarly here for we have here factor a, b and ab, for which we have computed the sum of squares under the partial confounding. So, that is going to be different than the SSA, SSB, SSAB that we used to do earlier, and each of them they are going to have the degrees of freedom 1 each, and then sum of square due to total under the partial confounding can be found, and then the SSE can be found by subtraction, and then the degrees of freedom for SS total, they are here 4 r star minus 1 in your earlier notation, but now this will be here 12 r minus 1, and if you try to obtain the sum of squares due to errors degrees of freedom, this will come out to be 6 r minus 3 or 2 r star minus 3. Now, after this you can just compute here different types of mean square just by taking the corresponding sum of squares divided by the degree of freedom. You can obtain here MS block due to replicates, MS block within replicates, mean square due to A, mean square due to B, mean square due to AB, and mean square due to error under the partial confounding. And after that you can construct the test statistics here F without any problem just by taking the ratio of the mean square error and the MSE, and you can find out their distribution, that is simply going to be F distribution under H naught, and you can conduct the test of hypothesis. So, I am not going to discuss it here, but rather I will prefer to consider here one more example of 2q factorial experiment, and on the similar lines we will try to see that how the terms are going to change. So, in this example we are going to do the same thing what you have learned in this example, but now I wanted to show you that how did that these different quantities are going to change. For example, you have defined here r star to be here 3 into r, but now in this case whether it will remain as 3r star or say 3r, or it will become 4r or something else, and how are you going to compute different types of effects, etc. So, once again, instead of going through the mathematical expression directly, we will try to understand them and we will try to develop them here. So, we consider here the setup of 2q factorial experiment, and the block size here is q square, and 4 replications are made as in this figure. So, we have here the replicate 1, replicate 2, replicate 3, replicate 4, just like as in earlier case we had only 3 replicates, and we have a confounded AB interaction effect in the replicate 1, AC in the replicate 2, BC in the replicate 3, and ABC in the replicate 4. Right. Now, you know means how are you going to assign different treatment combination to the different blocks depending on which effect is getting confounded, right. So, those things you can do here, and finally, you have here 2 blocks in replicate 1 in which you have here the treatment combination like this one in which AB is getting confounded. Similarly, you have here 2 blocks in each of the replicate 2, 3 and 4, and you have here different types of treatment combinations because you are trying to confound here different effects, right. Okay. So, now we have this setup. So, now before I go further, can we have this small discussion here? that now you can see here, you have here effects A, B and C, which are not confounded at all. Then we have here effect A, B, B, C and A, C, and they are including its generalized interaction that we are also trying to do here. So, they are getting confounded. So, that means if A, B is getting confounded in replicate 1, that means we can estimate it from the observations on from replicate 2, 3 and 4. And similarly for AC here, we can estimate AC from replicate 1, 3 and 4. And similarly BC can be estimated from replicate 1, replicate 2 and replicate 4, and similarly ABC can be estimated from replicate 1, 2 and 3. And now you see, you are also assuming that these are continuing and there are R repetitions. They are available for each of the replicate. So, you can see here this is continuing here R times, this is here R times, this is here R times, right. So, now altogether you have here 4 R number of these repetitions. Okay. So, now this arrangement of treatment in different blocks in various replicates is based on the fact that different interaction effects are confounded in the different replicates. Similar setup what we considered earlier, and the interaction effect as I shown you in this picture, AB is confounded in replicate 1, AC in replicate 2, BC in replicate 3 and ABC in replicate 4, and then we are trying to obtain the R replications of each blocks. They are obtained. That means there are total 8 factors involved in this case, including 1. Out of them the 3 factors A, B and C are not confounded, they are unconfounded, whereas the interaction like AB, BC, AC and ABC, they are partially confounded, right. Okay. So, now we want to estimate all these factors. So, definitely those factors which are not confounded, they can be estimated from all the replicates, right. If you remember that in the earlier lecture we had considered the case of estimation of the factor A, assuming that suppose it is not confounded. So, that is the same thing, same type of estimation will be executed here also, and for those effects which are confounded, they are going to be estimated from those replicates where it is not confounded. So, now you can see here that AB is going to be estimated from replicates 2, 3, 4, AC from replicates 1, 3, 4, BC from replicates 1, 2 and 4 and ABC from the replicates 1, 2 and 3. So, now first we try to consider the estimation of those effects which are not confounded. So, there are 3 factors A, B and C which are unconfounded. So, they can be estimated from all the 4 replicates. So, the estimation of the factor A from the jth replicate, where j is going from 1, 2, 3, 4 is as follows. This is exactly on the same line as we have done it earlier also, that the value of A from the replicate j, this is the linear function here, summation I goes from 1 to r, L transpose A j into y star I. Y star I is also a similar vector of observations on y, but now it will have 8 observations on 1, A, B, C, A, B, B, C, A, C, A, B, C, right. So, now if you try to find out this A from replicate 1, 2, 3, 4 and then you try to take its expectation. So, that is what we are doing here, that we are trying to find out the arithmetic mean of these 4 values. So, this will come out to be here, if I try to substitute here these values, it will come out to be double summation, j goes from 1 to 4, I goes from 1 to r, L transpose A j y star I divided by 16 r. And yeah, means I try to write down this summation here as a summation over I L A star transpose y star I, right. So, exactly on the same way as we have done it earlier. So, now this L A star will become here 8, 8, 8, 8, that is 32 by 1 vector. So, there are going to be 32 elements in the vector L A star, right, because each of this Laj is having 8 elements, which are all say plus 1 or minus 1. So, there are going to be 4 plus 1 and 4 minus 1 in each of the Laj. Now, how to find the sum of its squares due to A? That is now based on the 32 elements, which can be obtained here exactly in the same way as you have done it in the earlier case. That is summation over I L A transpose y star means over the I whole square divided by the total number of observation, which is here R into L A star transpose L A star, which is here 32 R, right. So, now you have obtained the effect and the sum of squares for the case when an effect is not confounded, and similarly if you can you can also find out its variance, assuming that variance of yj is sigma square and all yij's are independent, which was the usual case in any ANOVA model, right. So, you can write down here variance of A here as say 1 upon 16 R whole square into variance of this linear function, which is here. You can see here there are 32 terms. So, this will become a 32 R sigma square multiplied by 1 upon 16 R whole square. If you try to simplify, this will come out to be here 60 sigma square upon 8 R. Right. Now, the way you have estimated A, you can also estimate B and C, because B and C both are not confounded. So, the factor B can be estimated as the arithmetic mean of all the estimates of B from each of the replicate 1, 2, 3, 4, and we can write down here exactly in the same way B is equal to summation I goes from 1 to R L B star transpose y star I, where this L B star is going to be a 32 cross 1 vector as earlier, and it has 32 elements. So, now the sum of squares due to B can also be obtained exactly on the same line, that summation I goes from 1 to R L B star transpose y star I and its whole square divided by 32 R, right. And similarly, you can obtain the variance of B exactly on the same way, means I do not have to do any calculations. You already have obtained here, you can see this variance of A to be here sigma square upon 8 R, and A and B are similar. So, I can write down here directly the variance of B as sigma square upon 8 R. And similarly, the unconfounded factor C can also be estimated exactly on the same lines as you have estimated A and B. So, this is again the arithmetic mean of all the C estimated from each of the 4 replicates based on R observations. So, C can be also expressed exactly in the same way. Same summation I goes from 1 to R L C star transpose y star I. Yes, this L A star, L B star and L C star, they all will be having only 2 types of number plus 1 and minus 1, but their locations are going to be different, and we know how to write down the A B C in the case of 2q factorial experiment. So, this L star C will also have 32 elements in it, and that is going to be a 32 by 1 vector. Now, if you want to find out the sum of squares due to C, that is again exactly on the same line. You already have found this sum of squares due to B. You can see here like this one, and earlier you also found the sum of square due to A here like this one. So, I can directly write down here the sum of square due to C exactly on the same line as summation I goes from 1 to R L C star transpose y star I whole square divided by 32 R. And the variance of C, that is the same, that's as you have found here, the variance of A as sigma square upon 8 R, variance of B here sigma square upon 8 R. So, similarly, the variance of C is going to be here sigma square upon 8 R, no problem. Well, so now we have completed the the estimation, finding out sum of square, variance for those effects which are not confounded. So, now we come to the second part where we are going to do the same exercise for those effects which are confounded. So, first we consider the estimation of factor AB. So, the factor AB is confounded in the replicate 1. So, it can be estimated from the replicates 2, 3 and 4. And the final estimate of AB can be obtained as the arithmetic mean of these 3 estimates. So, I can write down here AB under the partial confounding, which is AB under and in the subscript this is here PC as AB from replication 2 plus AB from replication 3 plus AB from replication 4 divided by 3. Now, you can see here means earlier it was 4 because A, B, C were getting estimated from all the 4 replicate, but now you are estimating only from 3. So, this is the point where you have to be little bit watchful that what are you going to do, and based on that this number in the denominator that is going to be changed, right. So, you can see here in this case here this will become here 12R because AB rep from 2, 3, 4 they are going to be based only on 4 observations, right. So, now if you try to write down AB rep 2 here in the format of this linear function, AB rep 3, AB rep 4 in the format of linear function. So, I can just combine these 3 linear functions together as we have done in the case of 2 square factorial experiments, and you can see here then I am writing simply here LAB say transpose y star I and summation over I goes from 1 to R, where this L star AB is a vector which is containing all the elements of LAB2, LAB3 and LAB4. And so, obviously, this is going to be a 24 by 1 vector and it has 24 elements, right, because each of this LAB2, LAB3 and LAB4 has 8 elements into it. We can find the sum of squares due to this AB under the partial confounding. So, it is simply going to be like as this S is AB, and which is again on the same lines summation I goes from 1 to R L transpose star AB into y star I whole square divided by the total number of observations which are here R into L transpose star AB into L star AB, and this is actually here 24 R because there are 24 elements and there are R replicates. So, now and similarly the variance of this AB under partial confounding in this case is obtained under the assumption that Yij's are independent, they have got the same variance sigma square. So, we can find out here variance of AB under this partial confounding say here 1 upon 12 R whole square and variance of this entire linear function summation I goes from 1 to R L star transpose AB into y star I, and this if you try to see this function is the has 3 components. So, now the these 8 of these each of this function has 8 R elements and the covariance terms are going to be 0 because all Yij's are independent. So, I can write down here this 8 R sigma square first components, 8 R sigma square from the second component and 8 R sigma square from the third component. So, this is altogether 24 R sigma square upon 12 into 12 into R square, and if you try to solve it here this will come out to be here sigma square upon 6 R. So, now we can do a similar exercise with other effects that are confounded here AC and ABC. So, in case of AC this can be estimated from the replicates 1, 3 and 4 and then we try to take its arithmetic mean. So, it will be like as here AC rep 1 plus AC rep 3 plus AC rep 4 divided by 3. Now, you have to be careful here once again that you are dividing here by 3 because there are 3 types of ACs which you have estimated from different replicates. And if you just try to express all these things in the form of a linear function, this can be written as summation I goes from 1 to R L star transpose AC y star I divided by 12 R. So obviously this L star transpose AC is a vector of order 24 by 1, and the sum of squares due to this AC PC in this case can be found by the same expression, except that this L star is going to change here like this, right. So it will be summation I goes from 1 to R L star prime transpose AC y star I whole square divided by 24R. Okay, so now we have obtained this thing, and similarly we can obtain here the variance of AC under the partially confounded effects, assuming that all Yij's they are independent and each of the Yij's has got the variance sigma square. So as you have seen here in this case, you can see here you had found this variance to be here sigma square upon 6R. So without doing any algebra, I can also write down here this is going to be the same here also, because this AB and AC both are getting estimated from a similar setup with the same number of observation, only the replicates are different, right. So now we have obtained this variance also, and now the confounded effect BC can now be estimated from the replicates 1, 2 and 4. So that is again exactly on the same lines, that you try to take the arithmetic mean of BC from replicate number 1, 2 and here 4, and then try to take its arithmetic mean. So this denominator here is going to be 3. And suppose if this was not confounded, then the denominator is going to be here 4. So now if you try to express BC rep 1, rep 2 and BC rep 4 in the form of a linear function, and then you try to combine it, I can express it here in this format, summation I goes from 1 to R L star transpose BC y star I divided by 12R, right. So now all this component L star AC BC etc., they are going to have only two types of elements, +1 and -1, but their positions are going to be different, and this vector here L star transpose BC is again a 24 by 1 vector, which has here 8 elements from replicate 1, 8 elements from replicate 3 and 8 elements from replicate 4, right. So now similarly if you try to find out the sum of squares due to BC in this case, then it is going to be based on say 24R number of elements, and it is given here like this one, SS BC under the partially confounded effect is summation I goes from 1 to R L star BC transpose y star I whole square divided by 24R. And similarly you can also compute here the variance of BC under this case, means BC is partially confounded, and we are making here the same assumption that Yij's are independent and each of the Yij has got a variance sigma square. And if you try to obtain the variance, this will look like here this, right. So that is sigma square upon 6R, and this is again you can verify here that we had found here the same as variance of AC PC, and we had obtained here also as sigma square upon 6R. So need not to get confused that how I am writing it here without doing any algebra. And now finally the effect ABC is confounded in the replicate 4. So it has to be estimated from the replicates 1, 2 and 3. So we try to estimate this ABC from replicate 1, replicate 2 and replicate 3, and then we try to take its arithmetic mean. And this is how we are going to estimate the ABC under the partially confounded effects, and they are this ABC under rep 1, rep 2 and rep 3, they are going to be once again the linear function, and we try to combine those linear function, and we try to write down here, say here summation I goes from 1 to R L star transpose ABC y star I, where this L star transpose ABC is a vector containing of the vector L from this replicate 1, 2 and 3, each having 8 elements. So the order of this L star ABC vector is going to be again 24 by 1, and it has 24 elements. So, now in case if you want to find out the sum of squares due to ABC in this case, which is based on 24 elements, we can find out here like this linear function summation I goes from 1 to r L star transpose ABC y star I whole square divided by the total number of observation, which is here 24 r, right. So, now you have obtained the effect ABC, its sum of squares, and now we try to find out its variance. So, now you do not need to do any algebra to find out the variance. You already have found the variance when an effect is confounded in the it is confounded in the one replicate and it is being estimated from the 3 other replicates. So, the variance of ABC in this case, assuming that Yij's are independent and each of the Yij has got the variance sigma square. This variance can be found here as a variance of ABC under PCS sigma square upon 6r. Right. Okay. So, now if you try to see here, now if we try to compare first, that what if you are confounding these effects in all the replicates, or you are not going to confound these effects in all the replicates. You see, in case if you confound any of these effects in all the replicates, then the entire information about that factor is lost, and that is the case of complete confounding. And in this case, what are you trying to do? Out of 4r number of total replications, you are trying to confound only it into some part, right. So, now in case if we try to compare the variance of any effect which is confounded or not, then we try to compare their variances as follows. So, if an unconfounded design with 4r replication was used, then the variance of each of the factor A, B, C, AB, BC, AC and ABC is sigma star square upon 8r. Whereas you can recall that in the last lecture, when we considered the 2 square factorial experiment, we had just assumed the variance of Yij under the 2 square factorial experiment as sigma star square. So, similarly, we are assuming here to be here sigma star square is here, right. So, and this is based on the blocks of size 8, right. That is the case of complete factorial. And now you have estimated it on the basis of partial confounding. So, the relative efficiency of a confounded effect in the partially confounded design with respect to that of an unconfounded one in a comparable design is like this: 6r upon sigma square divided by 8r upon sigma star square. And if you try to simplify, this is coming out to be here 3 upon 4 sigma star square upon sigma square. So, now what is the meaning of this? So, the meaning here is that the information on a partially confounded effect related to an unconfounded effect is just 3 by 4, right. So, this means here what? That if you had confounded the effect in all the replicates, that is your complete confounding, then the information is completely lost. But you have confounded it only into one replicate, so you are able to have the 3/4 of the total information with you, right. So, now if you do not have any information, or if you have just 3/4 information, that is the decision which an experimenter has to take, right. What we are doing here, we are simply trying to develop here a methodology under which we can do such things, right. So, obviously, if sigma star square is greater than 4 sigma square upon 3, then the partially confounded design gives more information than the unconfounded design. Well, the statement what I just make about the 3/4 information is retrieved, that is assuming that both the setups have got the same variability, right. Now, we have obtained the different sum of squares due to those effects which are confounded and due to those effects which are not confounded. So, now we can obtain here the sum of squares due to blocks, and after that we can obtain the total sum of squares, and then we can obtain the sum of squares due to error by subtraction. So, that the Fisher-Cochran theorem holds true in this case also. So, now the next question is, how are you going to find out the sum of squares due to block? So, as we had discussed in the beginning of the lecture when we discussed the sum of squares due to block in the case of 2 square factorial experiment, we had divided the sum of squares due to block into 2 parts. Sum of squares due to block within replicates and due to replicates. Right. So, the same thing we are going to do here also, and if you try to recall that this was the algebra what we have done earlier, right. So, you do not get here confused, and if you try to see here, this is what we have done, right. So, this is the same expression what we have obtained here, we are going to use here, and earlier we had obtained this expression that sum of square due to block was divided into sum of square due to block with within replicates and due to replicates. So, the same thing we are going to do here also, right. So, now you can see here that we try to do the same algebra, and now we have the same result here. Say sum of square due to block is equal to sum of square due to block within replicates and sum of square due to block due to replicates, right. But in this case, now you have to see that the sum of square due to block within replicates, that is going to be a little bit changed, and for that you have to understand how you are going to find it out. You can see here it is 2 cube, and here the summation is going up to 4r, right, but the division of this block is in the same way, right. So, SS block WR is given by here 1 upon 8 summation I goes from 1 to 4r, B 1 I square plus B 2 I square divided by 2 minus R I square, and this carries here 4r degrees of freedom, and the sum of square due to replication here is like this one 1 upon 2 cube that you can see here, summation is going from 1 to 4r Ri square minus the correction factor. So, now you have to be careful here in the correction factor also. Now, you are here using the number of observation to be 32r, and this sum of square due to replication is going to carry 4r minus 1 degrees of freedom. And what about the sum of square due to total? That is going to be found exactly in the same way, that triple summation y square ijk minus the correction factor which is g square upon 32r, and g is simply here the sum of all the observation, triple summation ijk over y ijk. So, now you have obtained here the sum of square due to treatments. Well, you have divided it into say several components due to the effects which are confounded, which are not confounded. You have obtained here the sum of square due to blocks, and then you have again divided it into within replicates and due to replicates. You have obtained here the sum of square due to total. So, now what is left? SSE. So, SSE is going to be obtained by subtraction, that is SS total minus all sum of squares, because you can see here that you are going to have here different sum of squares due to A, B and C, A, B, B, C, A, C, A, B, C, but and depending on, because in this case they are going to contribute something. If this would had been the case of complete factorial, then all those effects which are confounded, they will not appear in the ANOVA table, but they will be the part of sum of square due to error. That is not really going to happen here. So, now I can combine all these things in this ANOVA table, analysis of variance table. So, now you can see here what are the courses here. They are the due to replicates, due to the blocks within the replicates, and corresponding to which we have the sum of squares due to block, but now sum of square due to block is also divided into two components, sum of square due to block due to replicates, sum of square due to block within replicates, and each of them is carrying a degrees of freedom here 4r minus 1 and 4r respectively, right. And then we have here three factors A, B and C which are unconfounded, and we have obtained their sum of square as say SSA, SSB, SSC, and that is exactly the same thing what you could had obtained the sum of squares as in the case of complete factorial case, when you are trying to use instead of r replicates you have more number of replicates which is 4r. So, and obviously this each sum of square here, this is going to follow a chi-square distribution with 1 degrees of freedom that you can write down here, right, because I am using it here again. So, that is why I am not giving you here the complete details. So, each of this SSA, SSB, SSC, this is going to follow a chi-square distribution with 1 degrees of freedom, and similarly now here AB, AC, BC and ABC. These are partially confounded, and based on that we have found the suitable sum of squares due to AB, AC, BC and ABC, right. They will also have a chi-square distribution with 1 degrees of freedom each, right, and all of them, all the sum of squares, they are going to be mutually orthogonal to each other. Well, I am not giving you here the proof, but you can thought in the same direction as we have used in the earlier analysis of variance case. And then we have obtained the sum of square due to total, and then SSE can be obtained by subtraction, so that the Fisher-Cochran theorem holds true. And yes, each of this SS sum of square, that is going to follow a chi-square distribution with their respective degrees of freedom, and the degrees of freedom for the sum of square due to total, this is 32 r minus 1, right, and by subtraction if you try to find out the sum of squares due to rest degrees of freedom, this is 24 r minus 7. Now, and yeah, obviously this each of the sum of square due to A, B, C, A, B, A, C, B, C, A, B, C, they will be carrying only 1 degrees of freedom. So, now you can obtain here the mean square due to block due to replicate, mean square due to block within replicates, then mean square due to A, mean square due to B, mean square due to C, mean square due to AB, mean square due to AC, mean square due to BC, mean square due to ABC, and mean square due to error. So, that is simply obtained by sum of squares divided by the degrees of freedom. Now, you are going to create different F statistics. All those theorems that SSE and the sum of squares, they are mutually independent, they are following chi-square distribution. So, we can create here a F statistic by taking the respective chi-square variable divided by the degrees of freedom, and based on that you will have here F statistics for factor A as FA, for B as FB, for C as FC, for AB as here FAB, for AC as here FAC, for BC here as a FBC, and for ABC here as a F of ABC, right. So, they are going to be simply obtained by here, for example, FA will be here MSA upon here MSE, right, and simply FB here will be MSB upon MSE, and so on here, right. Simply here MSABC will be here SSABC PC divided by SSE, right. So, and then they will have the degrees of freedom, which is say here the degrees of freedom of their sum of squares and SSE. For example, FA will follow F distribution with degrees of freedom 1 and 24 r minus 7 under H naught, and similarly here F ABC will also follow a F distribution with the degrees of freedom here 1 and 24 r minus 7 degrees of freedom under H naught. Right, and then based on that you can simply conduct the test of hypothesis for each of this effect exactly in the same way as you used to do in the past. Right. So now we come to an end to this lecture, and you can see here what I have done, means how I have handled this topic. That instead of giving you first the basic fundamental all sorts of theories and then giving you this idea that how are you going to compute this different expression, how are you going to handle the concept of partial confounding, etc., I have gone in the reverse direction. That I have taken here two examples, one from the 2 square factorial experiment and one from the 2q factorial experiment. And then I have tried to find out all the ingredients of the ANOVA table, which are here sum of squares, their treatment totals, and we also have found the variances so that we can compare the two situation if the effect is confounded or not, and that is also going to help you if you are going for the multiple comparison test. So now the main part which you have to understand here, that you means I know that you know how to compute the sum of squares, but what are the different adjustments which you have to make when you are trying to deal with the partial confounding, that you have to do it with your own hand, so that you can understand that sometimes I am trying to divide by 3, sometimes I am trying to divide by 4. So this is what you have to understand. Now, once you have understood rather that how you can handle this type of situation, now if I ask you, suppose you have here 3 replicates, replicate 1, 2 and 3. Now, replicate 1 is say repeated say R1 number of times, replicate 2 is repeated R2 number of times, and replicate 3 is repeated R3 number of times. Now, can you compute different estimates, sum of squares and variances? I'm sure yes. The only thing is will be that you have to be little bit careful that when you are trying to develop the linear functions like a summation Li yi, then you have to be careful that what is the order of this Li. That is the only thing where you have to be careful. And once you have developed these things, now conducting the analysis of variance is very simple. Okay, so now with this lecture, we come to an end to this course also. Well, if you try to see what we have done, we have first developed the tools, statistical tool for conducting the test of hypothesis, and then we have understood that how the data is going to arise when we want to use those types of statistical tool. Now, I am not saying at all that I have completed here all the topics which are available in the designs of experiment. There are many more topics, and these are the basic fundamental topics that without learning them you cannot learn the further topics. There are still many more topics like as partial BIBD, fractional replications, etc., many more. And beside those things, we have not considered the constructions of the design. That is a separate part. So now I believe that you have understood that the design of experiment is based on linear estimation, matrix theory, regression analysis, etc., and it is based on the solid statistical foundations, and it is equally applicable in the real life also. Without this, you cannot conduct actually any experiment, whether it is related to engineering sciences or biosciences or biostatistics, whatever you want. So that is why it is very important to understand these fundamentals so that you can develop something new, something better than this. So with this objective that you are going to learn more, you are going to develop something better for the welfare of the people, for the welfare of the country. I wish you all the best, and I pray to God that you do well in your life. May God bless you, and I will see you sometime somewhere. Till then, goodbye.